Welcome to this problem walkthrough. In today's session, we'll be tackling LeetCode problem number 1478, Allocate Mailboxes. This is an interesting optimization problem where we aim to minimize the total distance between houses and mailboxes while balancing constraints like the number of mailboxes available. Let's dive in and explore the solution. Imagine you are tasked with placing mailboxes along a street where houses are located at specific positions. These positions are given as an array called houses, where each element represents the location of a house. You're also provided an integer k, which tells you the maximum number of mailboxes you can install. The goal is to determine the minimum total distance between each house and its nearest mailbox. Total distance is calculated by summing up the absolute differences between a house's position and the position of its nearest mailbox. For example, if a house is at position 5 and the nearest mailbox is at position 3, the distance is 5, 3 equals 2. You need to minimize this total distance across all houses. The constraints ensure that the number of houses is between 1 and 100, their positions range from 1 to 10,000, and k is at least 1 but no greater than the number of houses. Finally, the output is a single integer representing the minimum total distance possible. Let's explore some examples to understand this problem better. In the first example, the houses are located at positions 1, 4, 8, 10, 20, and you are allowed to place 3 mailboxes, k equals 3. The optimal placement is at positions 4, 8, and 20. Now, calculate the total distance. The first house at position 1 is closest to the mailbox at position 4, so the distance is 1, 4 equals 3. The second house is at position 4, which matches the mailbox position, so the distance is 0. Similarly, the third house at 8 is directly at a mailbox, so the distance remains 0. For the fourth house at position 10, the nearest mailbox is at position 8, resulting in a distance of 10, 8 equals 2. And finally, the last house at position 20 is perfectly aligned with a mailbox, so the distance is 0. Adding these distances together gives a total of 3 plus 0 plus 0 plus 2 plus 0 is equal to 5, which is the output. In the second example, the houses are located at 2, 3, 5, 12, 18, and you are allowed to place 2 mailboxes, k equals 2. The optimal placement is at positions 3 and 12. For the first house at position 2, the closest mailbox is at position 3, so the distance is 2, 3 equals 1. The second house at position 3 is already at a mailbox, so the distance is 0. For the house at position 5, the nearest mailbox is still at position 3, resulting in a distance of 5, 3 equals 2. Next, the house at position 12 is perfectly aligned with a mailbox, so the distance is 0. Finally, the house at position 18 is closest to the mailbox at position 12, giving a distance of 18 and 12 equals 6. Summing these distances gives 1 plus 0 plus 2 plus 0 plus 6 is equal to 9, which is the output. Now, take a look at another example where there's only one mailbox allowed. In the third example, the houses are at positions 7, 4, 6, 1, and only one mailbox, k equals 1, can be placed. The optimal strategy is to place the mailbox at position 4, which is the median of the sorted house positions 1, 4, 6, 7. Calculating the total distance, the first house at position 1 has a distance of 1, 4 equals 3. The second house at position 4 is exactly at the mailbox, so the distance is 0. The third house at position 6 is nearest to the mailbox at 4, resulting in a distance of 6, 4 equals 2. Finally, the house at position 7 also has the nearest mailbox at 4, giving a distance of 7, 4 equals 3. Adding these up, the total distance becomes 3 plus 0 plus 2 plus 3 is equal to 8. This example highlights how the median minimizes the total distance when only one mailbox is allowed. The constraints and edge cases further reinforce the need for efficient placement strategies, especially when the number of houses or their distribution varies significantly. To solve the Allocate Mailboxes problem, the goal is to minimize the total distance between houses and mailboxes when k mailboxes are available. Several approaches can be considered. First, the brute force approach involves generating all possible ways to place k mailboxes, calculating the total distances for each configuration, and returning the minimum. While this method is mathematically correct, its time complexity of n to the power of k asterisk n is exponential, making it computationally infeasible for large inputs. Next, we have the greedy heuristic approach. Here, the houses are sorted in mailboxes or placed iteratively to minimize the local cost, such as by placing a mailbox at the median of a subset of houses. Although sorting takes O n log n, this approach does not guarantee a globally optimal solution, especially for multiple mailboxes. Finally, there's the dynamic programming approach. In this method, we define dp I, j as the minimum cost of placing j mailboxes for the first I houses. A crucial insight here is that the cost for a range of houses is minimized when a mailbox is placed at the median of that range. This allows us to pre-compute costs efficiently and significantly improves performance. To implement the dynamic programming approach, the solution follows a series of steps. First, the houses array is sorted. Then, the cost of allocating mailboxes for any segment, L, R, is pre-computed in O, n squared. This pre-computation allows us to efficiently calculate the range costs later. The dynamic programming transition formula is defined as dp I, j equals min, dp p, j1, plus cost, p, I, where p less than I in cost, p, I, is the pre-computed cost for the range, p, I. This formula ensures that the minimum cost is carried over as mailboxes are added incrementally. The time complexity includes O, n squared, for pre-computing costs and O, k asterisk n squared, for solving the transitions. While this approach may be slower for large values of n or k, it is efficient enough for typical problem constraints. The dynamic programming strategy is the chosen approach because it guarantees the minimal total distance while maintaining reasonable computational efficiency, which is essential for competitive programming. The insight that placing a mailbox at the median minimizes the cost for a segment is the cornerstone of this method, making it a reliable and practical solution. When comparing the different approaches, the trade-offs become clear. The greedy approach is faster, with a time complexity of O, n log n, but it is unreliable since it doesn't guarantee the optimal solution. On the other hand, the dynamic programming approach, though computationally more expensive, ensures an optimal solution with a complexity of O, k asterisk n squared. Compared to brute force, dynamic programming is exponentially faster while maintaining correctness, making it far more practical for larger inputs. Regarding space complexity, the dp table requires O, k asterisk n, space, which is manageable for most constraints. Overall, the dynamic programming approach provides the best balance between correctness, efficiency, and implementability. While it has a higher computational cost compared to greedy methods, its ability to guarantee the minimal total distance makes it the ideal choice for solving this problem effectively. In the Allocate Mailboxes problem, the objective is to strategically place k mailboxes along a street to minimize the total distance between houses and their closest mailbox. The problem is defined by two inputs, the houses array, which specifies the locations of houses on a one-dimensional street, and k, the maximum number of mailboxes we can allocate. The challenge lies in minimizing the sum of absolute distances between each house and its nearest mailbox. To solve this, the first step is to sort the houses array. Sorting is essential because it ensures that houses are in linear order, making distance calculations more systematic. The next step involves pre-computing the cost of assigning one mailbox to any subset of houses. Here's the key insight: if you place one mailbox for a group of houses, the optimal location for that mailbox is the median of the group. This is because placing the mailbox at the median minimizes the total absolute distance. To facilitate this, we create a 2D matrix cost, I, j, where each entry represents the cost of placing a single mailbox to serve houses in the range from houses, I, to houses, j. We compute the cost, I, j, by placing the mailbox at the median of the range and summing up the absolute differences between each house in that range and the median. This pre-computed cost matrix is a critical optimization that reduces redundant calculations later in the algorithm. Next, the problem is extended to handle k mailboxes using dynamic programming. The intuition is to divide the houses into k groups, where each group is served by one mailbox. To formalize this, we define a dp state, let dp m I represent the minimum cost of allocating m mailboxes to the first I houses. The base case is straightforward: if there's only one mailbox, the cost for the first I houses is simply cost 0, I1, since all houses must be served by a single mailbox. For the general case, calculating dp m I involves iterating over all possible breakpoints j, which represent potential divisions of the houses into groups. The recurrence is given by dp mi equals min dp mi dp m1 j plus cost j I1. This equation captures the idea of splitting the houses at j, assigning one mailbox to the range j plus 1 I, and combining it with the optimal solution for the previous m1 mailboxes. The final result for the problem is stored in dp k n, where n is the total number of houses. This dynamic programming approach avoids testing all possible ways to assign k mailboxes, which would be computationally expensive, by building the solution iteratively using overlapping subproblems. There are some critical insights that underpin this algorithm. First, placing a mailbox at the median of a group of houses minimizes the sum of absolute distances, which is why the cost I-J matrix is centered around medians. Second, the use of dynamic programming drastically reduces the need for exhaustive computations by breaking the problem into smaller, reusable subproblems. Finally, pre-computing the cost matrix ensures that the cost of placing one mailbox for any range of houses can be accessed in constant time, further improving efficiency. This entire approach relies on a few key data structures. The houses array must be sorted to facilitate median calculation. The cost matrix stores pre-computed costs for placing one mailbox in any range of houses, and the dynamic programming table dp mi tracks the minimum cost of allocating m mailboxes for the first I houses. The dp table, represented as dp mi, is the cornerstone of this algorithm. It allows us to efficiently calculate the minimum cost of placing m mailboxes for any given subset of houses. Let's now discuss the complexity of the algorithm. Sorting the houses array takes O, n log n. Pre-computing the cost matrix requires O, n squared, operations, as we compute the cost for all possible ranges of houses. Finally, filling the dp table involves O, k asterisk n squared, computations because, for each of the k mailboxes, we iterate over all possible breakpoints and house ranges. Combining these steps, the overall complexity is approximately O, k asterisk n squared. It's also important to consider edge cases. For example, if k is greater than or equal to the number of houses, the cost is 0 because each house can have its own mailbox. When k equals 1, all houses are served by a single mailbox placed at the median of the entire array. For unsorted input, we must ensure the houses array is sorted before proceeding. Finally, even if the house locations are sparsely distributed, the algorithm remains correct, as it inherently minimizes distances regardless of the spacing between houses. Here, we begin by importing the ru_cache decorator from the functools module, which will help us optimize our recursive function by caching results. Then, we define the solution class in the main function, minDistance, which takes two inputs, houses, a list of house locations, and k, the number of mailboxes we want to allocate. The houses list is sorted to simplify the calculations for placing mailboxes. Next, we define a helper function called compute_cost that calculates the cost of assigning houses within a specific range, from index I to j inclusive, to a single mailbox. The cost is minimized by placing the mailbox at the median house location in that range, as the median minimizes the sum of absolute distances. The function then computes this sum for all houses in the range and returns it. Afterward, we define a memoized recursive function dp, which will calculate the minimum cost of placing k mailboxes starting at house index I. The base cases for this function handle scenarios where we run out of houses or mailboxes. If there are no more houses and no mailboxes left to allocate, the cost is 0. However, if there are no more mailboxes but houses remain, the cost is set to infinity since it's impossible to allocate mailboxes in that situation. Finally, we initiate a loop where we attempt to allocate a mailbox for houses from I to j and recursively calculate the cost for the remaining houses and mailboxes. We keep track of the minimum cost encountered so far in a variable called min_cost. The loop continues by iterating through all possible ranges of houses, from index I to j, calculating the cost of placing a mailbox for those houses, and adding it to the result of the recursive call for the remaining houses and mailboxes. After exploring all valid ranges, the function returns the minimum cost computed. Lastly, we initiate the recursive process by calling the dp function with the starting index of 0 and the total number of mailboxes, k. This will calculate and return the minimum cost required to allocate k mailboxes optimally for the given houses. By leveraging memoization and the pre-computed costs, this implementation efficiently solves the problem while avoiding redundant calculations. Here, we begin the Java implementation of the Allocate Mailboxes problem. We first import the necessary utilities and define the min-distance method, which serves as the entry point for our solution. The method takes in an array of house positions and the number of mailboxes k. The first step is to sort the houses in ascending order to simplify calculations. Next, we pre-compute the cost of assigning all houses between indices I and j to a single mailbox. This is done using a nested loop, where for each range of houses, we calculate the median house position since the median minimizes the sum of absolute differences. This pre-computed cost is stored in a 2D array called cost. We then initialize a memoization table dp to store intermediate results, filling it with -1 to indicate that no values have been computed yet. Finally, we call a helper method, findMinCost, to calculate the minimum total distance using recursion and memoization. The findMinCost method is defined to handle the recursive logic of the problem. It takes the current house index I, the remaining number of mailboxes k, the sorted house positions, the pre-computed cost matrix, and the memoization table as inputs. The base cases are straightforward. If there are no houses left to process and we have used up all mailboxes, the cost is 0. Conversely, if we run out of mailboxes before placing all houses, the result is set to integer.max_value to indicate an invalid scenario. If the result for the current state has already been computed, we simply return the cached value from the DP table. Otherwise, we iterate through all possible ranges of houses starting from I, calculating the cost of placing a mailbox for the current range and recursively determining the cost for the remaining houses in mailboxes. The minimum cost across all valid placements is stored in dp, I, k, and returned. This approach ensures efficiency by avoiding redundant calculations while systematically exploring all possibilities. To solve this problem, we start with an example where houses are at positions 1, 4, 8, 10, and we need to allocate 2 mailboxes. First, we sort the houses, which in this case are already sorted. The total number of houses is 4, and we set up to allocate 2 mailboxes. Next, we pre-compute the cost of assigning a group of houses to a single mailbox. For example, if we look at the houses from index 0 to 1, the median house is at position 1, so the cost is 0. Similarly, for houses from index 0 to 2, the median is still 1, and the cost becomes the absolute difference of 1 from both 1 and 4, which sums up to 3. We continue this process for all valid subarrays. After pre-computing these costs, we start solving the problem recursively using dynamic programming. Starting with dp02, which means allocating 2 mailboxes starting from the first house, we explore placing the first mailbox for houses from index 0 to 1, which has a cost of 0. The remaining problem is then reduced to dp11, where we allocate 1 mailbox to the remaining houses. For dp11, placing a mailbox for houses from index 1 to 4 results in a cost of 4, leading to a total cost of 5 for this configuration. We track the minimum cost as we explore other options and eventually find the optimal solution. The result for this example is that the minimum cost to allocate 2 mailboxes for the given houses is 5. Now, let's consider another case where all houses are located at the same position, for instance, houses at 2, 2, 2, and we need to allocate just 1 mailbox. Here, since all houses are already at the same position, the sorted array remains 2, 2, 2, and the total number of houses is 3. With only 1 mailbox to allocate, we calculate the cost of assigning all houses to a single mailbox. The median house for the range of houses from index 0 to 3 is at position 2, and the cost is 0 because each house is already at the median position. Using dynamic programming, we start with dp01, which means allocating 1 mailbox starting from the first house. Assigning the mailbox to all 3 houses gives a cost of 0, and the remaining problem dp30 is trivially 0 because no houses are left. The total cost, therefore, is 0, which is the minimum cost for this configuration. The result for this edge case is that the minimum cost to allocate 1 mailbox for houses at 2, 2, 2 is 0. Now, let's examine a larger input where houses are at positions 1, 5, 9, 12, 20, and we need to allocate 3 mailboxes. First, we sort the houses, which are already in sorted order, and note that there are 5 houses in total. With 3 mailboxes to allocate, we pre-compute the cost of assigning different groups of houses to a single mailbox. For instance, for houses from index 0 to 2, the median is at position 5, and the cost is the sum of 1-5 and 5-5, which equals 4. Similarly, for houses from index 2 to 5, the median is at position 12, and the cost equals 9-12 plus 12-12 plus 20-12, which sums up to 11. We continue this process for all valid subarrays to prepare for the dynamic programming step. Using dynamic programming, we solve for DP03, which means allocating 3 mailboxes starting from the first house. We first try placing the initial mailbox for houses from index 0 to 2, which has a cost of 4. The remaining problem reduces to DP22, where we allocate 2 mailboxes to the remaining houses. For DP22, we place the next mailbox for houses from index 2 to 4, which has a cost of 3. The problem then reduces to DP41, where the final mailbox is placed for houses from index 4 to 5, with a cost of 0. Summing these costs gives a total of 4 plus 3 plus 0, which equals 8. Therefore, the minimum cost to allocate 3 mailboxes for houses at 1, 5, 9, 12, 20 is 8. The time complexity of the solution is governed by several components, and the first part involves sorting the houses. Sorting the houses array, which is necessary to simplify median calculations later, takes n log n, where n is the number of houses. This is a one-time cost incurred at the beginning of the function. Next, we have the pre-computing of costs using the compute_cost function. This function calculates the cost of assigning houses from index I to j to a single mailbox. Since the array is sorted, finding the median is O1, and summing the absolute differences between the median and the house positions takes j I plus 1. When this function is called for all possible pairs I, j, it results in n squared calls, and the total work here is n squared. These two steps lay the foundation for the dynamic programming solution. The dynamic programming step adds the most significant computational overhead. The dp(i)k function is memoized to avoid redundant calculations, and it involves iterating over all possible partitions by varying j from I to n1. For each subproblem, there are at most n choices for j. Since the dp state depends on both I, which can range from 0 to n, and k, which can range from 1 to k, there are n*k unique subproblems. For each subproblem, the cost computation involves a call to compute_cost, which is j I plus 1, or n in the worst case. This leads to n squared *k, total work for the dynamic programming step. Adding the sorting cost and the pre-computing cost, the overall time complexity of the solution becomes n cubed *k. The space complexity of the solution is determined by 3 main components. First, the memoization table for dp(i)k stores results for all unique states. Since there are n*k unique states, and each state requires 1 space, the total space used for memoization is n*k. Next, the pre-computed costs for all pairs I, j are stored in memory, which requires n squared space. Finally, the recursion depth of the dp function is limited by the number of houses n, which means the call stack consumes n additional space in the worst case. When we combine these, the total space complexity is dominated by n squared plus n times k. To understand the efficiency of the optimized solution, it helps to compare it with the brute force approach. A naive solution involves generating all possible ways to partition n houses into k groups, which results in an exponential number of partitions, approximately k to the power of n. For each partition, calculating the total cost, which involves summing distances, takes n. This gives a total time complexity of k to the power of n*n for the brute force method, which is infeasible for large inputs. In contrast, the optimized solution leverages pre-computed costs and dynamic programming with memoization to reduce the time complexity to n cubed *k. When k is large, such as k equals n, the best-case scenario simplifies the problem, as each house gets its own mailbox, and the complexity reduces to n log n for sorting. In the worst case, where k equals 1 and all houses share a single mailbox, the full n cubed time complexity from dynamic programming is realized. The mathematical proof of the complexity solidifies our understanding of where n cubed *k arises. First, during cost precomputation, the nested loops over all pairs I, j, result in O, n squared, combinations. For each combination, summing distances requires O, n, in the worst case, leading to O, n cubed, for this step. Second, the dynamic programming step ensures each subproblem is solved only once due to memoization. The maximum recursion depth is O, k, and for each state, there are O, n, iterations of the inner loop. This results in O, n cubed asterisk k, for the dynamic programming phase. Combining both steps confirms the total complexity is O, n cubed asterisk k, which is significantly more efficient than the brute force approach for practical inputs. When solving this problem, there are a few common mistakes to watch out for. First, not sorting the houses can lead to suboptimal solutions. Sorting ensures that you can calculate distances and place mailboxes in an order that minimizes the total cost. Always make sure to sort the houses array before proceeding. Another frequent error is confusing the median with the average. To minimize total distance, the median is the correct choice for placing a mailbox within a segment of houses. Using the average instead increases the overall distance, so always compute costs based on the median. Lastly, when using dynamic programming, poorly defined states can result in incorrect transitions. For example, if your DP state doesn't clearly represent the segment of houses or the number of mailboxes, your solution may not work as intended. A good state definition is DP, I, k, where it represents the minimum cost of placing k mailboxes for the first I houses. This clarity is essential for accurate transitions and results. Another mistake to avoid is not pre-computing the costs of placing mailboxes. If you calculate the cost for each segment of houses repeatedly during the solution, it can make the algorithm inefficient. Instead, pre-compute a cost table where cost, I, j, represents the cost of placing a mailbox for houses between indices I and j. This saves significant computation time during the DP transitions. Additionally, it's important to handle edge cases explicitly. For instance, if all the houses are at the same position, the optimal cost is 0 because no distance needs to be covered. Similarly, if there are fewer houses than mailboxes, you should limit the number of mailboxes to the number of houses. Overlooking these scenarios can result in incorrect outputs, so always account for these edge cases in your solution. There are key insights that can help you solve this problem optimally. First, the problem is best addressed using dynamic programming with pre-computed costs. This approach has a time complexity of O, n squared asterisk k, which accounts for both the DP transitions and the cost pre-computation. Second, understanding why the median minimizes absolute distances is crucial for deriving the cost function efficiently. This insight underpins the accuracy of your calculations. Third, always keep the problem's constraints in mind. For example, if the number of houses n or the number of mailboxes k is very large, brute force methods will be too slow, and optimizations like pre-computations become necessary. Lastly, during interviews, it's important to clearly explain how you define your dynamic programming states and transitions. Interviewers are often interested in how well you can articulate the reasoning behind your approach, so take the time to describe your process clearly. This problem is closely related to several others that can help deepen your understanding of similar concepts. For example, LeetCode 410, split array largest sum, involves dividing an array into k segments to minimize a specific cost, which is similar to this problem structure. LeetCode 2218, maximum value of k coins from piles, is another k partition problem solvable using dynamic programming. LeetCode 312, burst balloons, highlights the significance of pre-computing costs to solve subproblems efficiently. Lastly, LeetCode 131, palindrome partitioning, shares similarities in segmenting an array optimally using DP. When considering alternative approaches, brute force is the simplest. It involves trying all possible placements of k mailboxes and calculating the total distance for each configuration. However, this method is computationally infeasible for larger inputs due to its exponential complexity. Another option is the greedy approach, where you place mailboxes at locally optimal positions. While easier to implement, this method may fail to find the globally optimal solution, especially when non-local decisions are required. The most effective approach to solving this problem is dynamic programming with pre-computed costs. In this method, you define a DP state like DP, I, K, which represents the minimum cost of placing K mailboxes for the first I houses. The pre-computed cost, I, J, values help determine the cost of placing a mailbox in a specific segment efficiently. This approach guarantees the correct result and is computationally efficient, but it requires careful implementation to handle both the cost pre-computation and the DP transitions. While this method has a higher upfront complexity compared to alternatives like brute force or a greedy algorithm, it is the optimal choice for balancing efficiency and accuracy in solving the problem. Great work! We've covered how to solve the Allocate Mailboxes problem using dynamic programming. Remember the importance of breaking down problems into smaller subproblems and optimizing for specific constraints. Keep practicing, and don't forget to like, share, and subscribe for more problem-solving walkthroughs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!